Because a lot of the homework is literally so it's and then he doesn't, he purposely doesn't
Okay, let's get going. So thanks again for your questions. Unfortunately, as usual, there's not enough time to handle all of the questions, so I'll try my best. This is just the link to the coffee with the professor thing, so there's still some spots left. So just I would advertise for that one more time. So again, we'll get together and we'll have a free coffee with a couple of students. It'll be like me and 4 students or something. So let's just start with. So basically, I'm going to try to go through with what I thought were the more common questions. But this one was kind of a good one to start off with. So how do we know the eigenvalues of the spin eigenstates are plus or minus h bar? So if you go back in Griffiths, so when he talks about angular momentum, and so every book does this at some point, you can go through and get to the commutation relations for angular momentum, and then from there you can figure out the your eigenstates for angular momentum. And so back in chapter 4, when you do this, we're dealing with L. And so this is very much, from the hydrogen atom, and at this point you're thinking it much more in terms of orbital angular momentum, right? But the thing is, when you do this, basically, the angular momentum is quantized in orders of a half. So like the possible m's and l's and such you can have, the L's start at 1/2, and then go 1, and then basically they include all the different integers going up by 1/2. Now, orbital angular momentum, when you go through and solve it, it turns out that you're not allowed to have the half integers. Okay, but so back when they were developing this, they knew that there was this possibility to have these half in between. All right, and so when things like the Stern-Gerlach experiment came up, and also I believe Pauli got the idea because of the exclusion principle, right? He noticed that basically the way atoms were working, you can have 2 in all of these different states, and so it occurred to him, well, maybe we could use this spin 1/2 idea. All right, and so sort of coming from the fundamental angular momentum relationships, we know that there's a possibility to have spin 1/2, and then just once you have spin 1/2, your m is defined as either negative, should be careful, negative h bar over 2 and h bar over 2. So it basically comes out of these relationships that's possible. Again, we'll mention that when you get to relativistic quantum mechanics, which is quantum field theory, you can see a little bit better how the electron is prescribed. Again, the way that it works is you'll try to build versions of the Schrodinger equation that are relativistic, right, in energy. And all these equations, when you take the small limit, they basically come back down to the Schrodinger equation, but they're different for the different kinds of particles. And so the Dirac equation is what works, or what is the equation for an electron. And again, it works out that you see that the spin is going to be 1/2. And so for us, it's just sort of like prescribed. And just what is this idea of angular momentum again, or spin? It's a more innate quality of the particle itself, right? So the particle itself, you think about it having a mass and a charge, but it also has an angular momentum. All right, and all particles can have different kinds of angular momentum. So electrons have spin 1/2. Other particles have different kinds of spin. And we sort of use this analogy of it sort of like in our heads, kind of like a classical spinning ball. But of course, that's not correct. And in fact, there is no classical analog to this. And so kind of a weird thing that I thought would be fun to point out is just this idea. So if we look at the spin 1/2 particle, all right, so so imagine that you guys went through and you found the eigenvectors at some random angle. So we all together did the z, the x, and the y, and then you guys in the homework found the ones for some random angle. And so if you look at the spin state at some random angle, it comes out to be this here. So like spin up. And so there's some. So I'm just going to, just for the explanation today, only look at this in the xy axis. And so this here describes the state vector at some angle. All right, and so if I keep it here at z and put in 0 and 0, I get, what do I get? Well, let's just look at that real quick. If I do that, I get what you'd expect. So if theta equals to 0, this is 1, this is 0, and I basically just get, our vector 1, 0. So I get 1 here, because another way to write this would be cosine theta over 2 sine theta over 2. Now here's a weird thing. So let's look at theta 2 pi, all right? So if I do that in my picture, because, according to this picture here, if I do that, I come right back to the z-axis. But what happens if I actually plug this in to my deal over here? So here my vector would be like this. So now my vector at the angle of 2 pi, all right, if you look at it, it comes out to be negative 1, 0. Right? And that comes from these factors of theta over 2 in here, right? And so there's this discrepancy here between sort of the actual rotation I'm making in space and the rotation that my state vector is using. And so in fact, in order to get back to the original state vector, right, I need to actually rotate it 4 pi. So you'll hear some people talking about how an electron, so this idea of the different kinds of spin, one way to look at it is it tells you something about the symmetries of your particles. And so an electron is something that you'd have to spin around 2 times to get it back to where you started from, right? Which obviously there's nothing classical that acts that way, right? So anyway, I just thought that I'd throw that out there. But I think perhaps question.
So what's the difference between this one and if I theta?
I'm not sure what you mean, like the wiggle factor, or like,
If I theta, that one.
yeah. So I mean, you can write this in different ways, but for the spin 1/2, if I write the state vector, you're always going to get this factor of theta over 2 in there, right? It's kind of more of an aside. I just thought it was interesting to talk about. So I think pretty much the number one question I got was about composite states and combined states. So I thought it'd be good for us to kind of go through this. So when you're adding angular momentum, there's two kinds of states. And I think everybody has a good picture of what this is. The composite state is writing this when you're sort of viewing it very much as two separate particles. And the combined state is when you're looking at it as, you know, these two particles acting together as one entity. And we're going to find out, right? We haven't really done this yet, but we'll find out later that there'll be cases where you have to look at it one way or the other in order to figure out what you want to figure out. So it's an important thing to be able to do this. And so here is our composite state. So we started with just this idea. And again, these are just notes that we did before. This is literally just my notes that are online. So the composite state you write in this format here. And it's a little bit confusing, I think, but most people I've talked to got this down. And so basically, there's two quantum numbers that set the state for every particle, and that's the S and then the M. So S is, you know, what is the spin overall of the particle, and M is what's your component in the z direction. And so for the spin 1/2, you write out your sort of catch like this. And so I think one thing that can be kind of tricky is that, you know, just to make life easier, you know, we end up writing these things as up and down. But of course, when you get to something more complicated, like say adding 1 and 1/2, like we did in discussion, you can't do it that way, right? So you kind of have to look at it more like this way here. All right, so I think, you know, it's a lot of things that we're going to do where it's like, okay, you know, in this case, like the spin 1/2 version of adding two of these is, I would say, once you get it, you know, it's a certain level of rigor, but then going to anything else like the 1 and the 1/2 is sort of like, you know, more than double, I would think, just the complexity, just when everything, so it can kind of be tricky that way. And so we call this the composite state. So it's literally, okay, I've got these two spin 1/2 particles, and basically, you know, to set their state, I can just say one spin up and one spin down. Since we know that they're the same spin, we can kind of do that and be a little more loose about it. And so then, and so for instance, what you guys did in discussion, I think, so you had a spin 1 was 1, and spin 2 was 1/2. And so in this case here, there's 3 possible m's, and the 1/2 is just the same thing we just had. And so when you're writing your composite states, right, so we could just make an example. Say the one where the spin for particle 1 is 1, its component in the z direction is 1, and then here this would be 1/2, 1/2. And this would be, you know, like the top of the ladder state. But you could also write it sort of this way here. So we typically keep this here. And again, just because there's not really a great shorthand way of writing this with arrows, we do like that. All right, but that's how you could think about that. And that's the composite state. It tells you everything about the two particles, looking at them as individuals. And what we want to do is look at these, you know, be able to look at these also as combinations. So we make this grouping here. And so, for instance, so you got S1 squared, S2 squared, SZ1, and SZ2. So these are the individual pieces. And so when they're individual, this works very similar to the way it did before, right? So if I want to find, you know, here I want to find, okay, what's my state for particle 1, my spin state, S squared, right? I attack that into only X on the first part of your ket, and it gives you back, you know, your typical thing you'd get for S squared, and the same thing for SZ, all right? And so this is easier, I think, than finding out the totals that we'll do in a second. And so here's an example of something where you can go through and do that. And so in this case here, so again, So now I want to find, okay, what's the total SZ for this particle? And when we talk about total, we're looking at the combination of the two together. And so we did something like this in class. So if I'm looking at this particular state here, okay, the S1Z, again, only acts on the first particle. The S2Z only acts on the second. In this case, this guy's spin up, so I get h bar over 2. This guy's spin down, so I get negative h bar over 2. And so you're basically adding these two kets with h bar over 2, and you get 0. So you can think about that as 0 if you want times that ket, because it is that same ket there, just 0. And so in this particular case, the spin up and the spin down, the z component total is 0. And that one, I think, makes a lot of sense. It's just literally, you're looking at these two. If it was both spin up, you'd get h bar. If it's both spin down, you get negative h bar, and that sort of thing. So questions on this here, sort of figuring out, yeah, Ethan?
It's not specific to this, but when do you use like S and M versus NLM versus whatever else? I mean, I see the up and downs are kind of represented. But
So NLM would be when you're looking at an atom, right? So you have some sort of orbital. So what we're trying to do now, I mean, it's a good question. We're trying to sort of look at, okay, we have two spins or two angular momentums. How do we add them? And it's really natural to do that with 2 spin 1/2, right? Because we're going to use that a ton. But I would say moving forward from that, the big thing we want to do then is add together spins and angular momentums, orbital angular momentums. Because the big thing we're going to do moving forward from here is looking at atoms and sort of saying, what's the angular momentum of this atom? And so I want to be able to add together 2 different kinds. So we sort of start with this narrow thing, looking at 2 actual spins, and we're just going to get broader by looking at maybe adding the angular momentum for a whole atom or something. Which I think is what you're getting at. And we'll sort of, move into that more next. Abdullah, yeah.
So would the general wave function for the atom have a spatial NLM ket plus an SM?
Exactly. So we just, sort of touched on helium just really fast, at the end of last lecture. So we haven't really got too far. But yeah, exactly. So you would looking at that, you would have a spatial part which would involve L's and M's and N from what you did with the hydrogen atom, and then the spin stuff as well, right? And so we're sort of going to hit on that next. So this is kind of getting ready for that. We just haven't quite got there yet. And so here I just wanted to ask a question then. Okay, so we did that for SZ, and I think everybody seemed to kind of dig that. I think when people have been talking to me. And so now let's look at the other total, S total, where S total is the sum of S1 and S2. Okay, what do you get if you do S2 on these guys here? S squared would be the proper way to say that, right? Okay, so in the interest of time, I'm going to stop here. And if you do have your clickers, I'd love to participate just to kind of see. So I think we've got a polarized group here. So when I look at this here, so we got A. Okay, so who wants to tackle this one? Who wants to come at me and tell me what they were thinking on this one? Be brave without saying the answer. Yeah, James.
So if you look at the eigenstates of SC, so the up, up, and down, down are eigenstates, but then the up, down, and down, up are not. So A, B, C, D are like, they're all proportional to up, down, with 5 minutes.
Okay, I like that. Anybody else have a different thought? Yeah, Mohammed.
And that one that doesn't involve like actually going through the calculation.
Yeah, well, that's the thing. On this one here, you kind of, I mean, I'm sort of using the idea that you guys have actually gone through this calculation, which whether you remember or not, you did on your homework. But so if you actually do this calculation, right, and so this is the case, and we'll talk about this in a second, a little bit more in depth, but when you do this, it's actually pretty complicated, and your answer comes out to be something like this here. So if you take s squared times this, right, you get basically something times that initial ket, but also something times this ket as well. All right, and so it is not an eigenvector. So the total s squared is not an eigenvector of the composite states. And that's important because we're going to use that later on. And so that's key to kind of see that. So I think what James was saying was that idea there. And so the thing is if you remember, we spent some time talking about this. So this is a question about this. And so it's this idea here. So these spins, right? And so I'm totally agreeing that the spins sort of work this way. So you've got, your total spin is, S1 vector plus S2 vector. Where if I was to write this out, like the S1 vector would be something like Sx in the x hat direction, Sy in the y hat direction, and Sz in the z hat direction. So it's a three-dimensional vector. All right, and so when you square this business here, so what we're doing is we're actually literally to do this, we square this s squared, and so we're squaring this piece here. And this is the part that looks something like this here. So this is what, problem 5 of homework 2, you spent probably the most time doing this here, right? And so if you're looking at, so it's S1 plus S2 dotted with S1 vector plus S2. So you're thinking about this as a dot product. And so when you get the terms together, you'd say like S1 dotted with S1, S2 dotted with S2, and you get the two cross terms. When you dot a vector with itself, you just basically get back the magnitude. So we write that S1 squared. When you dot a vector with itself, you just get back the magnitude. And then here, you can look at these two guys. And since they act on different particles, they commute, and so you can write it as this cross term here. All right, and there's different ways to express this in discussion. We kind of brought up another one, but just the most sort of straightforward way is that these are two vectors being dotted, and let's see, just to be careful, when you're looking back at the notes later, you'd want to make sure that these are labeled 1, 2, and 3. Apologies for that. And so you've got literally just this dot product of the x, the y, and the z components. And so when you're that clicker question, to Mohammed's point that I just gave, was kind of a really mean one. But I gave it because I had thought, we'd done this before. It was still probably mean. But basically, you've got to act all three of these operators on that ket. And you'll find that when you do that, you don't get it to be an eigenvector. All right? And so it's kind of the thing that you've got to almost kind of remember. So questions on that? Yeah.
So like basically, if the z components of the spins of each particle is both well defined, the whole total spin is not.
Exactly. So the composite spin, and that's what we spend time finding these composite states to find a way to define that. And then those end up being a linear combination of our composite states, right? Yeah.
Yeah, another question. So, like the whole difference between composite and combined state, it's not just like different representations of the fundamentals are different, right? Because
sure. Yeah.
Because like that's the confusion I had, like when you use one versus the other. But I think like when if you can distinguish between the two, you can say like, oh, it's a spin upside down. But if you can't, then you have to use the combined state, which
yeah, and so and in some extent, that question I just asked, if you have them in the composite state, you can find s squared for the total thing. In general, if you have it in the compound state, you can find s squared total. If you have it in the composite state, you in general can't. So compound is thinking about this as like one entity. And one entity, you would know it's S and it's M, right? When you're doing composite, it's not as clear. Okay? Yeah, Mohammed.
Did you say the S1 squared and S2 squared are the magnitudes of S
Yeah, and so when you did this calculation, these were the easier parts, because these were just finding, your S squared operator for particle 1 and then for particle 2. This was the part that I think was a little bit nastier, at least that's my feeling. Okay, so just announcements real quick. So our test is on Friday. So we moved to a different, these rooms here, just because I'm a little worried about the space in here. So we'll see how it goes, but make sure you come to these rooms. Make sure you tell your friends who aren't here too. There's always like this possibility that someone comes here by mistake, and that's not good. That's the kind of thing I have like nightmares about, sometimes. So today's lecture and then discussion on Thursday, we're just going to do these all review, just to kind of see how that works. And so the policy for class is whenever it's a review, it's optional. So just so you know. And these are our extra office hours. Somebody pointed out that, so we all added an extra one. Is it this one here that's during 1:40? Yeah. So I emailed Sammy to switch to another one. So as soon as he gets back to me, we'll post that there. But so we're trying to saturate as much office hours as possible, and then also remember that Thursday from 5 to 7 they're going to go through a review, so they're going to kind of lead everybody through some problems there. So questions about the test? I posted the equation sheet. Someone's already suggested some things to add. I'm pretty flexible with that, so if you want to add more things to the equation sheet, let me know. Just do it soon before I print them off. Any other test questions? Okay. So here's just some questions just from last night. These are good questions. So someone asked about, I believe this is the Bell calculation that Griffiths did. So sort of the way I went through the different version of it in class was I think the one that Griffiths did is just a little bit above us, so I wouldn't ask any kind of questions about that. So here's another, I got a couple of questions like this. So here's someone, do we need to know about projection operators? It's mentioned in McIntyre but not in Griffiths. So this is kind of a tough thing to ask about. So in general, when I'm doing a test, especially when you guys are all physics majors, so I would feel okay asking a question about the projection operator only if I sort of in the question explained what it was, and then, so I would be okay with giving you guys kind of a new thing, saying, hey, here's this thing, here's how it works, try to do some calculations with it or something like that, right? Just to kind of, I would be okay with that. I would think it would probably be a hard question because you've never seen it before, but I would definitely not just say, projection operator, you should have read about this already in a different textbook, right? I would not do that. Right? Does that sort of make sense with that? So I don't like to sort of limit what I can say, just because, on this test, my goal is to give you some stuff that you've seen before, you feel comfortable with, and some stuff that you haven't seen before, to kind of see how you can synthesize this material in a new way. Okay, that's where the tricky part comes. So that's how I'd answer that. And this is another one I get. So can you post the answer and explanation for the clicker question? So first of all, so I post my notes, and with the podcast, I think you can pretty much go through and find the answers if you really need to. The problem with this, and this is a tricky thing, is that with these clicker questions, okay, I think the research shows that it's really important that you not know the answer when you're looking at it, right? Because because what can happen is if you know that it's A, you can sit there and convince yourself it's A, okay, and sort of miss the point of the question. And so what happens is if I make some nice PDF document of all the clicker questions and their explanations, it'll go to probably the class next year if I teach this again, right? And then it kind of ruins these clicker questions, right? And so I think from the podcasts, you can usually find the answers. We do it in class. Any of us will answer questions about it, but it's just like if you make this nice document, it kind of short circuits everything that we're trying to do. All right, so here's my rules for the test today. So this is just, important things to remember. So first, have a post-test plan. So I don't know, I remember when I had tests, right? Sometimes, like if I would sort of build my whole week around the test, I would plan and micromanage every minute, and then I'd walk out of the test and kind of just wander aimlessly for like a couple hours, and be like, wait a minute, what am I doing here? So it's good to have some sort of always dress nice. So I try to dress up and be real thankful to everybody because I understand all the work you're doing, right? And so I want to appreciate that. So this is for me, the hardest thing probably in teaching is finding the right balance in difficulty on the test, right? Our test is, in some ways, our best motivational factor, right? My goal here is to help all come together and learn some physics. And if you make a test that's too easy, what do people do? They're like, oh, that was really easy. I'm not going to do the reading for next week, right? And then if you make the test too hard, what happens? That was really hard. I'm not going to do the reading next week, right? Why even bother anymore? And so it's really tough. And especially, I'll warn you now, it's likely that I will probably mess this up the first time through. I'm going to try really hard not to. But if you're taking the test, like, wow, this is really hard, we'll take care of it later, right? We always curve things or whatever. So don't stress, but just to let you know, and it's not like I'm trying to be mean or show, whatever. And I think most people are like that. It's literally, sort of the guidepost we use to see how class is going. So, and it's tough. So please silence your cell phones. That's nice to do. So no matter what my face is doing, I'm not giving a hint. So one year, I think I was somebody, because people will ask questions, and usually the answer to the question is, I'm sorry, I can't really say much more about this, right? And so one year I was doing this, and I guess the guy thought I was like wiggling my eyebrows or something and giving him a hint or something. And so no matter what, I'm not doing that. Remember, I'm a physics person, so I don't know what's going on with my face, right? I can barely talk to people, right? Face to face. So when I was a student, I would like to listen to hardcore rap or heavy metal before a test, right? And the idea was to kind of pump yourself up. Because if you go to a test kind of worried, it's not really a good way to go in. So I would kind of come into the test thinking, you know what? This test disrespected my mother, and I'm going to teach this test a lesson, right? And finally, another rule I had was never talk about the test right after the test. Because they could just, you'll run into somebody that's like, oh, did you get the tricky part of number 2? And you're like, I thought number 2 was pretty straightforward. And then it kind of can ruin your weekend, right? So my rule is we'll talk about it later, but not right after class. Okay, so then what do you do? Well, and what was nice about number 5, okay, it was kind of a beast in the homework last week, but it gave you a way to sort of find these composite states using matrix multiplication and stuff. But the other way people do it is by raising and lowering operators. And so what you do is usually there's a couple states, basically they call this the top and the bottom of the ladder, that you can tell are related. Okay, because if I look at this one here, right, the down, if I take my SZ of this, I get negative H bar, which is, since I know one of my possibilities is a spin 1 particle with negative H bar as its M component, right, I know that those two have to be the same. So first of all, any questions about that? Is everyone, because there's only one composite state that has an M total of -1, so I know that these two have to be the same. And so in every set of these, you'll be able to find the top and the bottom of the ladder, hopefully. All right? And then what you do for this set is you just raise and lower it. So Griffiths, and typically, I don't know why, people like to lower them. I thought it'd be fun to try raising them. It's the same thing. And so I raised them, and I was able to get the next states. When you do the raising and lowering here, again, I'm not saying it's easy, but you can go through and get the 1, 0 state. You can do it again and get the 1, 1 state. Okay? So questions on that? So that's sort of the way we do that. Yeah, Ethan.
It was related to the discussion when we had someone come to this. So Sammy had mentioned that by figuring out that above was the highest rung of X, we could correlate that to figuring out what it would be for instead of 1, -1, what the highest would be for 1/2 1, or sorry 1/2 0 or something like that for the other spin state.
Yeah, so I want to talk about that too. So I think I would say this is the easier way to do it, or the easier ones to find. So here, you can do this. You can find the 1 states pretty easily, right? And then, but the next one is where it gets tricky, which I think is what you're talking about, right? So in here, right, what's really nice is for these states here. Okay, so generally we knew there was one more state, and we knew that it had to be orthogonal to these guys, right? And so the thing is so now with this other state. Okay, so I know it had to be 0, 0. And so the first step of this is realizing, okay, my possible kets that could make up this state are these two guys. right? Can someone tell me why that is? Why is this not a possible ket for this state here? Can anyone tell me that? Yeah, James.
Because the m's have so
Yeah, so I want both of these kets to have total spin of 0, and this is up a half, down a half, total spin 0, down a half, up a half, total spin of 0. Okay? And so this one would not be included. And so right away, which I think is what you're getting at, is that you can look at here and say that I know that this is some linear combination of this. Now initially, you can't right away, for most of these, figure out what those factors outside are. And that's the hard part. That's the case where in this version, it's pretty easy. I mean, in this version, you could almost write it down right away. But in that, that next hardest version, the 1/2 and 1, it's not as easy. So first of all, I want to apologize on that discussion, and this is my fault. I'm writing these. I probably should have put something in there to help you kind of get to, because you were doing the, what is it? So it was like the 3/2 states and then the 1/2 states. So I should have put something in there to help you find those 1/2 states. So on Friday's test, if I was to do something like that, I would definitely give you more help to get there, because it was kind of a beast to do that. So that, again, apologies for that. I mean, I sort of figure with discussion time, since Sammy and Dashwan are there, you guys can have it. It's a little more flexible, but yeah. So does that kind of answer your question? And so the idea is then you basically just know what the kets are, and you want to find them that's orthogonal to these guys. And I'm not saying it's easy. That's the really hard part. And so, yeah. So questions on, yeah, Abdullah.
If we have a 4-dimensional Hilbert space, does that mean we have 4 kets?
Yeah.
spanning that?
Exactly. Yeah. And so this is a 4-dimensional. This Hilbert space of these two particles has 4 kets. And so either way, it's got 4 kets. Either way, you do a composite or combined. Now, this is the easiest one to figure out. It's also, you could argue, the most important, because we're going to use it a ton, as we move forward from here. Okay. So questions on that? Let me see. The other thing too. So in this problem, you ended up with a matrix that looked like this here. This is another thing that in retrospect, I probably would have added something else to this. So I don't expect you to be able to find the determinant of a general 4x4 matrix. Okay? But in this case here, does anybody know of any hints how to handle a matrix that looks like this here? So anybody? Yeah, James.
Can you just expand along the rows close to the zeros? So take the determinant of the 2, and it's just 2 times the determinant of the 3 by 3, that 3 by 3 is the other 2.
Yeah, so that's exactly right. So there's tricks, like basically in this case here, you can think about it as 2 of these things. You already know the eigenvalues. You know that it's 2 and 2 for those ones that are diagonal. And it's that, they call this a block diagonal matrix. And so the 2 and the 2, and then what you can do is say, well then, it turns out that all I want to do then is diagonalize this matrix, which is a 2 by 2. Okay, so sort of this one and this one, you already know, right? But that other one then would be, and so it's much easier to do this than it is to do that one. So again, it's something I probably would have put more information in there for that, so apologies. Yeah.
So if I tried to add a -1 at certain positions, can you do that? Do you know what the rate for that is?
So you can sort of take the determinant, right? But the determinant will end up being 2 minus lambda times the determinant of this guy times 2 minus lambda, right? But since, and the thing is, what are we trying to find? We're trying to find the eigenvalues, right? So I don't necessarily care, because if it's a negative, you're going to equal it to 0 or something, right? Yeah, Muhammad.
By the way, this the combined states there for when you have 2 spin-half particles, right?
Yeah. So this was that, again, that problem 5 that I've been referencing a lot. Okay, so now this, I think, slides nicely into a discussion of symmetric versus antisymmetric states. So somebody asked that. And so I thought, and they asked a good question, just, how does this work for particles that are identical, but also particles, they call them different, but basically distinguishable. Okay? And so let's look at this here. So in class, I forget, a couple of lectures ago, we looked at this one here. And so for 2 spin 1/2 particles, which one of these are 2 spin 1/2 in the infinite square well, what are the possible states? Okay? And if you look at this here, we came out with this one here being the only possible state. Okay? And that's, again, since these are identical spin 1/2 particles, right, they have to be in a state that has negative, a negative eigenvalue with the exchange operator. All right, so it has to be antisymmetric, right? And we sort of discussed how this one here is antisymmetric where the other ones aren't. So first of all, is everyone okay with that? Yeah.
When you say the first one is an antisymmetric, is it like, is the spin or the wave function, like, you can't define it like that or something like that?
So this one here? Well, yeah, so this one's sort of broken in a lot of ways. But basically, if you look at this one here, right, so it needs to be antisymmetric. And so if I exchange the particles, these two exchange and that part is symmetric, right? But this part over here, if I exchange that, it's neither symmetric or antisymmetric. It's just like a different state, right? So that's sort of broken. That wouldn't be anything for like a boson or a fermion, right? So it's just sort of nothing. Whereas like, and then this one here actually works out to be the same way, okay? So the spins I can change. The spin is symmetric, but this guy here is neither symmetric or antisymmetric. If I change x1 and x2, I just get a different state. So that's the one thing, is that sometimes it's neither, right? I think we're sort of, used to being one or the other, but it doesn't have to be one or the other. Whereas in this one, so here if I change both of these guys, it's the same function here. And if I exchange these, I can arrange this to be the same function times a negative. Okay? Everyone okay with that? Yeah, Mike?
Say they're distinguishable, you don't need to be
Well, so that's, you read my mind. So let's do this. If they are distinguishable 1/2 particles in this well, okay, we can totally do that, all right? And so we'll change this problem here, because I think that's what the crux of this person's question was, to say 2 distinguishable. So like maybe one's an electron and one's a neutron or whatever, who knows? Okay, so what would happen in that case there? What would happen to this problem? Okay, this is going to kind of... Okay, so I should have read this before. Let's say all of the above, which kind of gives it away. But yeah. I was trying to be slick. I was like, I'm going to do my question as a clicker question. But basically, if they're distinguishable, we don't have this requirement, right? So basically anything that we're going to allow for the infinite square well would be okay. Okay, so this requirement is only necessary when you have identical particles. Okay, you got to have this symmetrization requirement when you have identical particles. Okay, so questions on that? So the answer here would just be this new all the above that I just introduced. Okay, let's try this one.
Question?
Sorry, yeah.
For 3, can you actually distinguish between the 2, like for the previous question?
So what about it now?
So for the previous one?
Yeah.
So for 3, which is like an 2 identical particles, can you actually distinguish between, I think.
Okay, but so the question is though, like if it's an allowed state.
Yeah, but then it won't be like 2 distinguishable particles.
Okay, but well, okay, why not though? I mean, because they're like one's like a neutron and one's an electron or something, right?
They're like, they're like in an antisymmetric state, so if you use the P operator, just like swap them, it's the same. So.
Let's talk about it afterwards, okay? So now just the same thing for the bosons. And so what do we think for the bosons here? Okay, so let's see what everyone thought and then talk about this one. So I'll call time. Oh. And so I think the majority I agree with. So let's look at this. So this is a boson, which means it has to be a totally symmetric state. So the same sort of thing I was talking about before, but now we want the eigenvalue to be positive. And so here, so if I switch these two, that's the same function. If I switch those two, it's the same function. So this is symmetric with exchange. This one down here, the same sort of idea. If I switch these two, that's symmetric. And if I switch these two, because there's a positive sign, that's symmetric as well. And then over here, what would we need to do over here? We would need to write out one of those states where it's like psi1, psi2, and then plus, psi1, psi2 of the two particle positions switched, right? But the idea is, for me, when I do a problem like this, I look at it and say, okay, let's apply the exchange operator. If I get positive 1, that could be a boson state. If I get negative 1, it could be a fermion state, all right? Yeah, Ethan.
When you say switch, do you mean like literally switch both the S and M, or just switch the M?
So the actual sort of states. So like right here, I would switch the x1 and the x2.
Right.
And then here you'd be, so this is like the 1 and the 1 are saying this is a spin 1 particle.
Yeah.
And so I'd be switching the 1 and the 0.
Okay.
Right, which in effect is switching the Ketz itself. So your answer is sort of both in this case, yeah. Matthew.
So for number 1, is it still like, even though you're describing the wave function of whole systems, it's still valid to use, or to have the spin or the wave function be in the composite state? Like, or does it have to
Yeah, I mean, so we never said with the composite state, like it has to be, like with the composite states, we literally, when we built those, we said 2 spin 1 particles. We never said they had to be identical or non-identical. We just did it for in general, right? And so then the thing is when building your actual states for the system, that's where you got to start thinking about the symmetry, whether they're identical or non-identical. Okay? Does that make sense? Yeah, Mohammed.
By the way, what clued you in that this that these particles has a boson, and what clued you from step 2 that they had to be fermions? Sorry.
Since there's spin 1, like there's
Yeah, so it's, in this case, it's told to you. And so there's a problem. One of the homeworks in problem set 3 is basically doing the full solution of these 2 clicker questions. So if you're a little mixed up, I would go through that one. The solutions are up, and it's basically it has an infinite well, and it says find me the states for distinguishable particles and identical particles. And so it goes through and does this. Here we're sort of looking at ones that don't work, but there it kind of sets it all up. Okay, so I think we'll stop it there just because, so I'll just be up here if you have questions, and we'll see you guys next time. Again, come to office hours and review sessions. We're hoping that you got lots of time to answer all your questions.
I'm trying to visualize like a whole lot of this.
So when we're talking here, we say that we're saying that the ground state would be like, what's the state, like the bottom state? Like the state that once you're in it, you can't get lower than that. Right? And so if there's a certain state, so like in this case, like the infinite square well gives us a state 1, right? And so in theory, both particles could be in that one state. Yeah, but it's possible, like sometimes you'll see questions where they do it where it's like, they'll say, it's really weird, they'll say like, spinless